Earthquake prediction is a branch of the science of seismology concerned with the specification of the time, location, and magnitude of future earthquakes within stated confidence limits but with sufficient precision that a warning can be issued. Of particular importance is the prediction of hazardous earthquakes likely to cause loss of life or damage to infrastructure. Earthquake prediction is sometimes distinguished from earthquake forecasting, which can be defined as the probabilistic assessment of general earthquake hazard, including the frequency and magnitude of damaging earthquakes in a given area over years or decades. It can be further distinguished from earthquake warning systems, which upon detection of an earthquake, provide a real-time warning to regions that might be affected. In the 1970s, scientists were optimistic that a practical method for predicting earthquakes would soon be found, but by the 1990s continuing failure led many to question whether it was even possible. Demonstrably successful predictions of large earthquakes have not occurred, and the few claims of success are controversial. Extensive searches have reported many possible earthquake precursors, but, so far, such precursors have not been reliably identified across significant spatial and temporal scales. While part of the scientific community hold that, taking into account non-seismic precursors and given enough resources to study them extensively, prediction might be possible, most scientists are pessimistic and some maintain that earthquake prediction is inherently impossible. Evaluating earthquake predictions. Predictions are deemed significant if they can be shown to be successful beyond random chance. Therefore, methods of statistical hypothesis testing are used to determine the probability that an earthquake such as is predicted would happen anyway. The predictions are then evaluated by testing whether they correlate with actual earthquakes better than the null hypothesis. In many instances, however, the statistical nature of earthquake occurrence is not simply homogeneous. Clustering occurs in both space and time. In Southern California, about 6% of M3.0 earthquakes are followed by an earthquake of larger magnitude within 5 days and 10 kilometers. Quote, in central Italy, 9.5% of M3.0 earthquakes are followed by a larger event within 30 kilometers and 48 hours. While such statistics are not satisfactory for purposes of prediction, they will skew to the results of any analysis that assumes that earthquakes occur randomly in time. For example, as realized from a Poisson process, it has been shown that a naive method based solely on clustering can successfully predict about 5% of earthquakes, slightly better than chance. As the purpose of short-term prediction is to enable emergency measures to reduce death and destruction, failure to give warning of a major earthquake that does occur, or at least an adequate evaluation of the hazard, can result in legal liability, or even political purging. But warning of an earthquake that does not occur also incurs a cost, not only the cost of the emergency measures themselves, but of civil and economic disruption. False alarms, including alarms that are cancelled, also undermine the credibility, and thereby the effectiveness, of future warnings. The acceptable trade-off between misquakes and false alarms depends on the societal valuation of these outcomes. The rate of occurrence of both must be considered when evaluating any prediction method. In a 1997 study of the cost-benefit ratio of earthquake prediction research in Greece, Stathosteros suggested that even the excellent prediction method would be of questionable social utility, because organized evacuation of urban centers is unlikely to be successfully accomplished, while panic and other undesirable side effects can also be anticipated. Quote, He found that earthquakes kill less than 10 people per year in Greece, and that most of those fatalities occurred in large buildings with identifiable structural issues. Therefore, Styros stated that it would be much more cost-effective to focus efforts on identifying and upgrading unsafe buildings, since the death toll on Greek highways is more than 2,300 per year on average. He argued that more lives would also be saved if Greece's entire budget for earthquake prediction had been used for street and highway safety. Instead, difficulty or impossibility. Earthquake prediction may be intrinsically impossible. It has been argued that the Earth is in a state of self-organized criticality, where any small earthquake has some probability of cascading into a large event. It has also been argued on decision-theoretic grounds that prediction of major earthquakes is impossible. However, these theories and their implication that earthquake prediction is intrinsically impossible are still disputed. Prediction methods. Earthquake prediction is an immature science. It has not yet led to a successful prediction of an earthquake from first physical principles. Research into methods of prediction therefore focus on empirical analysis, with two general approaches, either identifying distinctive precursors to earthquakes, or identifying some kind of geophysical trend or pattern in seismicity that might precede a large earthquake. Precursor methods are pursued largely because of the potential utility for short-term earthquake prediction or forecasting, while trend methods are generally thought to be useful for forecasting long-term prediction or intermediate-term prediction. Precursors. An earthquake precursor is an anomalous phenomenon that might give effective warning of an impending earthquake. Reports of these, though generally recognized as such, are only after the event, number in the thousands, some dating back to antiquity. There have been around 400 reports of possible precursors in scientific literature of roughly 20 different types, running the gamut from aeronomy to zoology. None have been found to be reliable for the purposes of earthquake prediction. In the early 1990s, the IASPEI solicited nominations for a preliminary list of significant precursors. 40 nominations were made, of which 5 were selected as possible significant precursors, with 2 of those based on a single observation each. After a critical review of the scientific literature, the International Commission on Earthquake Forecasting for Civil Protection concluded in 2011 there was considerable room for methodological improvements in this type of research. Quote, in particular, many cases of reported precursors are contradictory, lack a measure of amplitude, or are generally unsuitable for a rigorous statistical evaluation. Published results are biased towards positive results, and so the rate of false negatives is unclear. Animal behavior. For centuries there have been anecdotal accounts of anomalous animal behavior preceding and associated with earthquakes. In cases where animals display unusual behavior some tens of seconds prior to a quake, it has been suggested they are responding to the P wave. These travel through the ground about twice as fast as the S waves that cause most severe shaking. They predict not the earthquake itself that has already happened, but only the imminent arrival of the more destructive S waves. It has also been suggested that unusual behavior hours or even days beforehand could be triggered by foreshock activity at magnitudes that most people do not notice. Another confounding factor of accounts of unusual phenomena is skewing due to flashbulb memories. Otherwise unremarkable details become more memorable and more significant when associated with an emotionally powerful event such as an earthquake. A study that attempted to control for these kinds of factors found an increase in unusual animal behavior in one case, but not in 4 other cases of seemingly similar earthquakes. changes in VP versus. VP is the symbol for the velocity of a seismic P wave passing through rock, while versus is the symbol for the velocity of the S wave. Small-scale laboratory experiments have shown that the ratio of these two velocities, represented as VP versus, changes when rock is near the point of fracturing. In the 1970s, it was considered a likely breakthrough when Russian seismologists reported observing such changes in the region of a subsequent earthquake. This effect, as well as other possible precursors, has been attributed to dilatancy, where rock stressed to near its breaking point expands slightly. Study of this phenomenon near Blue Mountain Lake in New York State led to a successful prediction in 1973. However, additional successes have not followed, and it has been suggested that the prediction was a fluke. The VP versus anomaly was the basis of a 1976 prediction of a M5.5 to 6.5 earthquake near Los Angeles, which failed to occur. Other studies relying on quarry blasts found no such variations, and an alternative explanation has been reported for such variations as have been observed. Geller noted that reports of significant velocity changes have ceased since about 1980. Radon emissions. Most rock contains small amounts of gases that can be isotopically distinguished from the normal atmospheric gases. There are reports of spikes in the concentrations of such gases prior to a major earthquake. This has been attributed to release due to pre-seismic stress or fracturing of the rock. One of these gases is radon, produced by radioactive decay of the trace amounts of uranium present in most rock. Radon is useful as a potential earthquake predictor because it is radioactive and thus easily detected, and its short half-life makes radon levels sensitive to short-term fluctuations. A 2009 review found 125 reports of changes in radon emissions prior to 86 earthquakes since 1966. But as the ICEF found in its review, the earthquakes with which these changes are supposedly linked were up to 1,000 kilometers away months later, and at all magnitudes. In some cases the anomalies were observed at a distant site, but not at closer sites. The ICEF found no significant correlation. Another review concluded that in some cases changes in radon levels preceded an earthquake, but a correlation is not yet firmly established. Electromagnetic variations. Various attempts have been made to identify possible pre-seismic indications in electric resistive, or magnetic phenomena. The most touted, and most criticized, is the Van method of Professors P. Vorotsos, K. Alexopoulos and K. Nomikos Van, of the National and Kapodistrian University of Athens. In a 1981 paper they claimed that by measuring geoelectric voltages, what they called seismic electric signals, they could predict earthquakes. In 1980s the Van team published more on the research, and in 1990s they claimed they were able to predict earthquakes larger than magnitude 5, within 100 kilometers of the epicentral location, within 0.7 units of magnitude up to several weeks beforehand, and published a series of predictions. Objections have been raised that the physics of the Van method is not possible, and the analysis of the propagation properties of SES in the Earth's crust claimed that it would have been impossible for signals with the amplitude reported by Van to have been transmitted over the several hundred kilometers distances from the epicenter to the monitoring station. It was also claimed that Van's publications do not account for possible sources of electromagnetic interference. Taken as a whole, the Van method has been criticized as lacking consistency in the statistical testing of the validity validity of the hypothesis. In particular, there has been some contention regarding the catalogue of actual seismic events to use in vetting predictions, and of the predicted magnitudes. A critical study found that, because of such ambiguities, a set of 22 claims of successful prediction by Van were actually 74% false, 9% correlated at random, and for 14% the correlation was uncertain. Both positive and negative views on Van are summarized in the 1996 book, A Critical Review of Van, edited by Sir James Lighthill, and in a debate issue presented by the journal Geophysical Research Letters that was focused on the statistical significance of the Van method. Van had the opportunity to reply to the critics in those review publications. Sayur has subsequently suggested that a significant problem is that the vast majority of seismic data gathering stations are sensitive only to seismic and geodetic data, and not configured to detect geo-electromagnetic signals or other precursors. Therefore, the required data for comprehensive and definitive studies does not exist. Since 2001, the Van Group has introduced a concept they call natural time, applied to the analysis of the precursors. Initially it is applied on SES to distinguish them from noise and relate them to a possible impending earthquake. In case of verification, natural time analysis is additionally applied to the general subsequent seismicity of the area associated with the SES activity, in order to improve the time parameter of the prediction. The method treats earthquake onset as a critical phenomenon. An overview that presented the current status of Van research efforts supporting the Van results has been published by Hu Wang in 2015. After the 1989 Loma Prieta earthquake occurred, a group led by Anthony C. Fraser Smith of Stanford University reported that the event was preceded by disturbances in background magnetic field noise as measured by a sensor placed in Corralitos, California, about 4.5 miles from the epicenter. For the 5th of October, they reported substantial increase in noise in the frequency range 0.01 to 10 Hz. The measurement instrument was a single-axis search coil magnetometer that was being used for low-frequency research. Precursory increases of noise apparently started a few days before the earthquake, with noise in the range 0.15 Hz rising to exceptionally high levels about 3 hours before the earthquake, though this pattern gave scientists new ideas for research into potential precursors to earthquakes, and the Fraser-Smith et al. Report remains one of the most frequently cited examples of a specific earthquake precursor. More recent studies have cast doubt on their connection, attributing the Corralitos signals to either unrelated magnetic disturbance or, even more simply, to sensor system malfunction. Trends. Instead of watching for anomalous phenomena that might be precursory signs of an impending earthquake, other approaches to predicting earthquakes look for trends or patterns that lead to an earthquake. As these trends may be complex and involve many variables, advanced statistical techniques are often needed to understand them. Therefore, these are sometimes called statistical methods. These approaches also tend to be more probabilistic, and to have larger time periods, and submerge into earthquake forecasting. Elastic rebound. Even the stiffest of rock is not perfectly rigid. Given a large force, the Earth's crust will bend and deform. According to the elastic rebound theory of Reid, eventually the deformation becomes great enough that something breaks, usually at an existing fault. Slippage along the break allows the rock on each side to rebound to a less deformed state. In the process, energy is released in various forms, including seismic waves, the cycle of tectonic force being accumulated in elastic deformation and released in a sudden rebound is then repeated. As the displacement from a single earthquake ranges from less than a meter to around 10 meters, the demonstrated existence of large strike-slip displacements of hundreds of miles shows the existence of a long-running earthquake cycle. Characteristic earthquakes. The most studied earthquake faults appear to have distinct segments. The characteristic earthquake model postulates that earthquakes are generally constrained within these segments. Is the lengths and other properties of the segments of fixed earthquakes that rupture the entire fault should have similar characteristics. These include the maximum magnitude and the amount of accumulated strain needed to rupture the fault segment. Since continuous plate motions cause the strain to accumulate steadily, seismic activity on a given segment should be dominated by earthquakes of similar characteristics that recur at somewhat regular intervals. For a given fault segment, identifying these characteristic earthquakes and timing the recurrence rate should therefore inform us about the next rupture. This is the approach generally used in forecasting seismic hazard. UCERF3 is a notable example of such a forecast prepared for the state of California. Return periods are also used for forecasting other rare events, such as cyclones and floods, and assume that future frequency will be similar to observed frequency to date. The idea of characteristic earthquakes was the basis of the Parkfield prediction. Fairly similar earthquakes in 1857, 1881, 1901, 1922, 1934, and 1966 suggested a pattern of breaks every 21.9 years, with a standard deviation of plus or minus 3.1 years. Extrapolation from the 1966 event led to a prediction of an earthquake around 1988, or before 1993 at the latest. The appeal of such a method is that the prediction is derived entirely from the trend, which supposedly accounts for the unknown and possibly unknowable earthquake physics and fault parameters. However, in the Parkfield case, the predicted earthquake did not occur until 2004, a decade late. This seriously undercuts the claim that earthquakes at Parkfield are quasi-periodic, and suggests the individual events differ sufficiently in other respects to question whether they have distinct characteristics in common. Further research into the Parkfield seismic data revealed that several 4.0 earthquakes had reduced the stresses on the northwest portion of the Parkfield segment, causing it to skip generating the predicted 6.0 earthquake. The failure of the Parkfield prediction has raised doubt as to the validity of the characteristic earthquake model itself. Some studies have questioned the various assumptions, including the key one that earthquakes are constrained within segments, and suggested that the characteristic earthquakes may be an artifact of selection bias and the shortness of seismological records. Other studies have considered whether other factors need to be considered, such as the age of the fault, whether earthquake ruptures are more generally constrained within a segment or break past segment boundaries. Has a direct bearing on the degree of earthquake hazard. Earthquakes are larger where multiple segments break, but in relieving more strain they will happen less often. Seismic gaps. At the contact where two tectonic plates slip past each other, every section must eventually slip, as none get left behind, but they do not all slip at the same time. Different sections will be at different stages in the cycle of strain accumulation and sudden rebound. In the seismic gap model, the next big quake should be expected not in the segments where recent seismicity has relieved the strain, but in the intervening gaps where the unrelieved strain is the greatest. This model has an intuitive appeal. It is used in long-term forecasting, and was the basis of a series of circum-Pacific forecasts in 1979 and 1989 to 1991. However, some underlying assumptions about seismic gaps are now known to be incorrect. A close examination suggests that there may be no information in seismic gaps about the time of occurrence of the magnitude of the next large event in the region. Statistical tests of the circum-Pacific forecasts shows that the seismic gap model did not forecast large earthquakes well. Another study concluded that a long quiet period did not increase earthquake potential. Seismicity patterns. Various heuristically derived algorithms have been developed for predicting earthquakes. Probably the most widely known is the M8 family of algorithms developed under the leadership of Vladimir Borik. M8 issues a time of increased probability alarm for a large earthquake of a specified magnitude upon observing certain patterns of smaller earthquakes. Tips generally cover large areas for up to 5 years. Such large parameters have made M8 controversial, as it is hard to determine whether any hits that happened were skillfully predicted, or only the result of chance. M8 gained considerable attention when the 2003 San Simeon and Hokkaido earthquakes occurred within a tip. In 1999, Borik's group published a claim to have achieved statistically significant intermediate-term results using their M8 and MSC models, as far as worldwide large earthquakes are regarded. However, Geller et al. Are skeptical of prediction claims over any period shorter than 30 years. A widely publicized tip for an M6.4 quake in Southern California in 2004 was not fulfilled, nor two other lesser-known tips. A deep study of the RTP method in 2008 found that out of some 20 alarms, only 2 could be considered hits. It concluded that RTP is not significantly different from a naive method of guessing based on the historical rate seismicity. Accelerating moment release, also known as time to failure analysis, or accelerating seismic moment release, is based on observations that foreshock activity prior to a major earthquake not only increased but increased at an exponential rate. In other words, a plot of the cumulative number of foreshocks gets steeper just before the main shock. Following formulation by Bowman et al. Into a testable hypothesis and a number of positive reports, AMRA seemed promising despite several problems. Known issues included not being detected for all locations and events, and the difficulty of projecting an accurate occurrence time when the tail end of the curve gets steep. But rigorous testing has shown that apparent AMRA trends likely result from how data fitting is done, and failing to account for spatio-temporal clustering of earthquakes. The AMRA trends are therefore statistically insignificant. Interest in AMRA has fallen off since 2004. The occurrence of foreshocks has long been thought to be the most promising avenue in predicting earthquakes. A foreshock is a smaller earthquake that can strike minutes or days before a larger one. Because the rupture process for the earthquakes is still not completely clear, foreshock occurrence may give clues into an earthquake triggering process. In the non-critical precursory accelerating seismicity theory, foreshocks happen because of the constant build-up of pressure along the fault lines. This theory is given weight due to seismic measurements. This had led to the conclusion for some scientists that foreshocks are a precursor to a larger event, and should be further studied and considered in earthquake prediction.